So let's just go back to our loops a little bit. We found the magnetic field at the center of a loop and on the axis of the loop. What about the magnetic field in other places? Well, you could find that magnetic field by tracing it with a compass or by just using iron filings. That's what our picture is here. So the thing that looks like copper colored, that's just a metal loop and that's got a current going through it. Let's say that the current is coming down on the top. And that's in the vicinity of some iron filings. So those iron filings trace out the magnetic field. So through the center, it goes straight on through. That's what we found by doing our Biot-Savart law. And on the sides, it tends to curve. Goes up around this way, and then on the bottom kind of does the same thing, symmetric on top and bottom, of course. So that's the magnetic field around a current loop. We can also draw that out, and I nabbed a picture from your book to draw that. So there's a picture taken straight from your textbook. So the magnetic field lines are given there in blue. And the current, if you look really closely at the top of the current loop, you see a little dot that shows that the current is coming towards you. If you look at the bottom, you see a little X that tells you that the current is coming away. So this is telling you that the current direction is in this direction. So what you might notice here is this looks an awful lot like a bar magnet. One of the first pictures we presented when we started this chapter. So that looks like a bar magnet where this is the north, the magnetic field lines go out of the north and they go into the south. That's like a bar magnet. That's the picture from on top of the loop. Of course, it's also interesting if you look at the loop edge on. So if you put your eye here and look at the loop, what you'll see is when you look inside the loop, the magnetic field lines are coming towards you. When you look outside the loop, those magnetic field lines tend to go away from you, and we can draw that view on the other page. So this is an edge-on loop. So what we can say now is that since the little current loop produces a magnetic field, it looks like a magnet. So our little current loop actually pretends to be a magnet. It looks like a magnet. And we can quantify the nature of that magnetic field using something called the magnetic dipole moment. And this is a good description as long as we have smallish loops so that our radius is smaller than the distance where we're trying to measure the field. Just before we discuss the magnetic dipole moment, I'm going to flash us back to when we discussed the electric dipole moment. An electric dipole moment was a way to describe the electric field of two charges that were equal and opposite and they were close together. So if we wanted to find the electric field that was a distance x away, we knew that that depended on something called the dipole moment and the distance from the charge. The dipole moment had a symbol of P, and it was equal to the charge, the magnitude of the charges, times the distance between them. So an electric dipole moment is a way to talk about the electric field around charges. Next, we're going to move on to talk about the magnetic dipole moment, which is a way to talk about the magnetic field around current loops. Magnetic dipole moment, it's got the symbol of the Greek letter mu. It is a vector, so it has a vector sign. So let's develop our magnetic dipole moment. Let's begin with going back to our current loop. If we have a current coming around, and the radius of our current loop is r, then we can find the magnetic field at some point P using the process we've gone through already. We know that that magnetic field is all in the x direction. So there's the magnetic field B. That's some distance x away from the center, and it is on axis, so we're talking about the magnetic field on the axis here. And that magnetic field vector we found to be mu naught times I times r squared, over 2 times x squared plus r squared to the 3 over 2, and it was all in the x direction. So there's the general form of the magnetic field due to a current loop. When we're talking about a magnetic dipole moment, we're going to restrict ourselves to small loops. So we're going to say that x is pretty big compared to the radius of the loop. What does that mean about the expression for our magnetic field? Well, if x is pretty big, then x squared plus r squared is about equal to x squared. So the r term is not so important. That means that x squared plus r squared to the 3 over 2 is about equal to x squared to the 3 over 2, which is equal to x cubed. So as long as our distance is far away compared to the radius, our denominator now is going to simplify a bit. So let's put in our approximation. So this gives us for our magnetic field is approximately equal to mu naught times I times r squared over 2 times x cubed. And that's in the x direction. Okay, let's do a little bit of math. I'm going to multiply by 1. So I'm going to multiply by 2 pi, and I'm going to divide by 2 pi. I'm just going to move that 2 pi inside. I'll put it in front of my r squared. I'm hoping that 2 pi r squared jumps out at you. And then 2 times 2 pi gives me 4 pi in my denominator times x cubed, and of course that's in the x direction. So 2 pi times r squared is 2 times pi r squared. Pi r squared, that's the area of our circle, or the area of the loop. So mu naught times I times 2 times a over 4 pi times x cubed in the x direction. So now this is an expression for the magnetic field as long as we're kind of far away. Turns out that this is true regardless of shape. It doesn't have to be circular. You can prove it's true for other shapes as well. Okay, so now we'll introduce our definition of the magnetic dipole moment. So we'll define mu is equal to current times the area vector. Area is definitely a vector. It has a well-defined direction. It's always perpendicular to the object, and to get the orientation, so for example in our loop shown, is it to the right or is it to the left, what you do is you use a right-hand rule where you curl your fingers, make a circle with your fingers, with the current, and your extended thumb shows the area vector or the mu vector. So now let's insert this into our expression. So I times A is our mu vector. So for our result, our magnetic field is mu naught over 4 pi times 2 times mu, our magnetic dipole moment, over x cubed. So that's similar to our electric dipole. So something just to be real careful of here is mu naught and mu are not the same thing. Mu naught is our constant. It's the permeability of free space. Mu is current times area, and that's the magnetic dipole moment. So on our next page, we'll just do a summary of that right-hand rule because I know it feels like there's a lot of them coming at you. For a recap of that right-hand rule, let's say we have a current loop and the current is coming around in this direction. You make a circle with your fingers and you make your fingers go with the direction of that current. Then you stick out your thumb and your thumb shows the direction of the magnetic dipole moment. So if the current comes around this way, do a circle with our fingers this way, stick up our thumb, we see it point straight up, that's the direction of the magnetic dipole moment.